Alright, so let's start with the next chapter in the series of chapters. This is an important chapter. I'll be talking about materials which are used in the field of orthodontics. Now, if we talk about materials used in orthodontics, there are n number of materials, small materials, small appliances, and the materials and the material which are used to make those materials. We'll be talking about the properties of those basically in this chapter. So coming to the introduction, as I said, we have got plethora of orthodontic materials in use. How to classify them? So the first and foremost method of classification is according to the structures of orthodontic materials and according to the usage of orthodontic materials. Now, according to structures, we have got metallic materials, ceramic materials, and polymeric materials. And according to the usage, we have got wire alloys, which can be metallic wires, non-metallic wires. Then we have got orthodontic brackets, which can be made of stainless steel, titanium, plastic or polycarbonate, and ceramic brackets. Then we have elastomeric ligatures and chain, which are known as orthodontic auxiliaries, orthodontic adhesive composites, resins, cements, which can be used, and finally we have miscellaneous materials like alginate impression materials, brass lock pins, and so on. Right? So we have got classification according to structure and according to the applications. Now, coming to impression materials, first and foremost, the most common impression material used in the field of orthodontics is an alginate. Now, as we have talked about earlier in the chapter on essential diagnostic aids and model analysis as well. So, alginate is one of the most important materials to obtain a proper impression of the upper and lower teeth, and that impression can be utilized in the making of the cast. That is the replica of your jaws, of your patient's jaw. So what are the ideal requirements of orthodontic impression materials? It should be viscous enough to be held in the tray. It should not be too much flowy. It should conform itself to the dental and soft tissues, and it should have dimensional accuracy when it is stored for sufficient time duration. The material should flow and wet the oral tissues to be recorded adequately. The material should have enough elasticity and tear strength. Then that should be able to be removed from the undercuts without any significant distortions, and it should not undergo any dimensional changes, which should be compatible with the gypsum products. The gypsum products are the ones which are used to pour the impression, the dental stone, type 3, type 4, type 5 dental stones, right? And this chemical reaction is what is showing the chemical reaction what is taking place in an alginate. So I'm not going to much detail. I think this would have been covered in the chapters on dental materials, impression materials in dental materials chapter. So basically what we are trying to say here is that first and foremost there are two reactions, that is the precipitation of calcium phosphate delaying the formation of calcium alginate gel, and finally the second reaction leads to formation of calcium alginate gel. That is what you obtain once the alginate is set within the patient's mouth, and that is what you can remove from the patient's mouth, and that is ready for pouring using a dental stone. Okay. Now, what are the composition of dental impression material? That is the alginate. We have got sodium or potassium alginate. We have got calcium sulfate, dihydrate or hemihydrate, which acts as a reactor. Then we have diatomaceous earth, that is the silica. Basically, this is the silica, which acts as a filler, and you can see this has a significant contribution in the alginate according to weight by volume ratio. Then we have got zinc oxide. We have got potassium titanium fluoride, which acts as an accelerator and gypsum hardener. Then we have got sodium phosphate, which acts as a retarder. This can be asked as an MCQ question either in ortho or in dental materials, so please make a note of it. Then we have glycol to make the powder dustless, ammonium salt and chlorhexidine, and coloring and flavoring agents, obviously for obvious reasons, right? So these are the composition of alginate material according to the weight percentage. Now coming to elastomeric impression materials. Now they are a grade better in replicating the oral structures when compared to alginate on certain parameters. What are those parameters? They are hydrophobic except polyether. Then they have got high tear strength. They're specifically used in aligner cases. Nowadays, instead of taking impression of the mouth, we have got intraoral scanners available. I've just recently bought a scanner, so I'll be talking about it in the chapter on miscellaneous topics later on. That's when I'll be talking about how to use the scanner, what are the different methods of usage of scanner later on. Then they were the first polysulfide materials to be introduced, followed by condensation silicone and polyether. So polysulfide were the first elastomeric impression to be introduced. They are divided into addition and condensation silicones. Addition silicones are little better in terms of dimensional accuracy because there is no byproduct. In condensation silicone, ethanol is what you get as a byproduct, which has a tendency, which is very volatile and it's get evaporated, and that causes shrinkage of the impression. And many times this shrinkage of the impression causes dimensional inaccuracies in the prosthetic work what we get from the lab, or even in aligner cases. I faced this clinical situation, this troubleshooting problem in one of my cases earlier. So I don't use condensation silicones at all in my practice. Then addition silicones are also known as polyvinyl siloxanes. Okay. Now coming to materials for bite registration. Registration of three-dimensional relationship between the articulating surfaces of the upper and lower teeth is known as bite registration. What is bite registration? How the teeth are articulating with each other. That is what is being shown using a bite registration material. Now we can make use of impression plaster, zinc oxide eugenol paste, casting wax, or from base paste wax, and we can also use addition silicone, condensation silicone, even polyether materials, which can be available as interocclusal registration materials. They are specifically marketed as interocclusal registration materials, and this this bite registration is required in maximum number of aligner cases, even for fabrication of myofunctional appliances on a articulated dental cast, right? So for that purpose, we need materials for bite registration in the clinical practice. Now coming to gypsum products, as I said earlier, gypsum products are the one which are used to make the dental stones, dental casts. So their most important application is in the construction of working or study models. Type 3 plaster or type 1 dental stone is usually used in the construction of working models, and whereas type 1 impression plaster can also be used as interocclusal registration material, as I said earlier. Impression plaster. This is called type 1 impression plaster. Alright. Now coming to brackets and bracket materials. What are the brackets? Brackets are nothing but they are small. Either they can be made of metal or plastic or ceramic brackets, which everybody must have seen, or even most of you, or even some of you must have undergone braces treatment also during your teenage time, even during your college hours. So they can be classified based on material used for manufacturing of those brackets into metal brackets, plastic brackets, and ceramic brackets. Now in metal brackets, we have got stainless steel brackets. Stainless steel brackets, why? Because they are made up using stainless steel material. Gold coated brackets, platinum coated brackets, and titanium brackets. Then plastic brackets, we have got polycarbonate brackets, polyurethane composite brackets, thermoplastic polyurethane brackets. And ceramic brackets, we have got monocrystalline alumina, polycrystalline, and polycrystalline zirconia brackets. Now monocrystalline alumina brackets are clearer as compared to polycrystalline ones. Reason being, monocrystalline, as the name suggests, it has got a uniform distribution of the crystalline alumina. Alumina is aluminum oxide, right? So it has got uniform distribution of aluminum oxide particles within the substance of the bracket. Whereas polycrystalline one, it has got multiple types, multiple opacities, and that renders this polycrystalline alumina bracket little opaque. It is white in color for sure, but it is not completely transparent. It is either opaque or it is white in color. Okay. Now, this table shows composition of metals used in manufacturing of bracket. Actually, there is a numbering system. American Institute of Steel, something like that. AISI, American Institute of Steel. I am not remembering the other full form of I. So, based on the composition, based on the other characteristic features of that stainless steel, those stainless steels are numbered according to the AISI specification as 303, 304, 316, and so on. And based on that, based on the different composition, based on different desirable properties, the metallic brackets are made up of using these series of stainless steel brackets. Now, types of stainless steel, we have got austenitic stainless steel, which are denoted by 300 series according to AISI specifications. Martensitic steel, that is specified by 400 series. Ferritic steels, duplex steels, precipitation hardenable, that is called PH steels, cobalt containing steels, and manganese containing steels. So steel is the primary product. These are all additives into it. Now, a small MCQ, direct MCQ. Stainless steel was first made by Harry Brearley. Please remember this name. This was the person who was the first inventor of stainless steel. So types of ceramic brackets we have talked about earlier. I'll delete this particular box later on. Now, a significant property of stainless steel is the passivating effect. That is of clinical significance also in the clinical practice. Now, what do you mean by passivating effect? Basically, stainless steel is not resistant to tarnish and corrosion. It is not at all resistant to tarnish and corrosion. What is tarnishing and corrosion of steel? Tarnish and corrosion is an electrochemical process which degenerates the properties, which degenerates the quality, which degenerates the strength of a particular metal over time once it is exposed to the environment. Any environment. It could be atmospheric environment, it could be environment within the oral cavity, or any part within the body, right? So, resistance to tarnish and corrosion of stainless steel is because of the passivating effect of the chromium. Now, stainless steel has got carbon, iron, chromium, and nickel added into it. Carbon, iron, chromium, and nickel. So these are the four elements which are the primary elements in the alloy called stainless steel, right? Yeah, one more MCQ I have found. Out of these four, which is the maximum? Which component is the maximum? So many people end up marking chromium. I've seen in my college, many people end up marking chromium, whereas it's iron which is present in the maximum quantity, maximum amount in any given quantity of stainless steel. So please make a note of it. This is an MCQ based question. So coming back to passivating effect, it is because of passivating effect of the chromium. The chromium in the stainless steel forms a thin, transparent, adherent, but tough and impervious oxide layer on the surface of the alloy when it is subjected to an oxidating atmosphere as mild as clean air. So basically what is happening, how does passivating effect take place? So basically, you must have seen rusting. Everybody must have seen rusting. So why rusting is happening? Iron, when it comes in contact with oxygen, gives rise to iron oxide, right? This is what is happening, iron oxide. But under the influence of chromium, whenever chromium is present, so chromium, it preferentially reacts with the oxygen present in the atmosphere to form chromium oxide. Now this chromium oxide is what is responsible for the passivating effect. This layer of chromium oxide, it forms on the surface of the stainless steel when it is subjected to an oxidating atmosphere such as clean air. This protective layer prevents further tarnish corrosion by blocking the diffusion of oxygen to the underlying bulk alloy. Now this effect is known as passivating effect. Did you get me? What did I say? There is a preferential reaction of chromium with the oxygen to form chromium oxide. This chromium oxide is what is responsible for passivating effect. It forms a passivating layer on the surface of the stainless steel which does not allow further diffusion of oxygen molecules in the atmosphere further into the bulk of the metal, into the bulk of the rod. Suppose you have talking about an iron rod. So this prevents the further tarnish and corrosion. That's why this phenomena is known as passivating effect of chromium. Now for this effect to take place, a minimum of 12% of chromium is required. This is an MCQ question. Please remember, if the oxide layer is ruptured by mechanical or chemical means, a loss of protection against corrosion results. Hence, corrosion occurs if this layer is lost, and you can see in an iron rod, you can see the corrosion in the form of rusting. Everybody must have seen that, I'm sure of it. Now, there is something known as, there are two processes: sensitization and stabilization. There are two processes known as sensitization and stabilization. So till now we were talking about chromium getting in contact with oxygen to form chromium oxide. But what happens at the grain boundaries? This is the internal structure of a bulk metal. So we have got grain boundaries which act as an electrochemical cell having a cathode and an anode. Now what happens here? At the grain boundaries, chromium preferentially comes in contact with carbon. You know, carbon is already present in the stainless steel. So chromium comes in contact with carbon preferentially, leading to formation of chromium carbide. Chromium carbide is formed at the grain boundaries. It gets precipitated at the grain boundaries, which reduces the strength of the bulk material. So this chromium carbide is an enemy to the structural integrity of the iron rod. Now, how to combat this? This process is known as sensitization. Chromium, once it comes in contact with carbon, it leads to formation of chromium carbide at the grain boundaries, which is the enemy of the structural integrity of the bulk metal. So this process is known as sensitization. How to overcome this process? That is overcome by means of stabilization. Stabilization is done by addition of certain parts of titanium within the stainless steel. Titanium is added. Titanium gets preferentially reacted to carbon, leading to formation of titanium carbide instead of chromium carbide at the grain boundaries. And this titanium carbide does not cause any structural deformation to the bulk metal. Once the titanium carbide is formed, it leaves the chromium unreacted, and hence the unreacted chromium gets available to the atmospheric oxygen to form the passive layer of chromium oxide on the surface of the bulk metal. Hence, stabilization is promoting passivation. That's why the addition of titanium, it increases the life of the metal. It increases the life of the iron rod used in construction businesses also. Right? So that is the fundamental principle between sensitization, stabilization, and passivation. So please remember, this can be asked as an MCQ also. And in your final year university exam, these three processes can be asked as short note in your exams as well. Now coming to materials used for enamel preparation before the bonding. This slide is important because I have seen MCQ coming out of this particular slide. As I said earlier, this particular chapter is quite important. We have certain direct MCQs picked up. We have certain application-based MCQs picked up from this particular chapter. Okay. So what are the materials used for enamel preparation before bonding? That means for acid etching. What are the different steps in bonding? I'll be just coming to it. Just in a few slides from now. So what are the methods of enamel etching? First is phosphoric acid, 37% phosphoric acid etching for 15 seconds, followed by washing with running water for 10 to 20 seconds. Now I'm not going to detail what are the histochemical processes behind phosphoric acid etching. We have got type 1, type 2, type 3, type 4 types of honeycomb pattern of the enamel. I'm not going to that detail. Then second option is we have got sulfated polyacrylic acid, and this process is known as crystal growth theory, which was given by Major and Smith in the year 1986 in a article published in American Journal of Orthodontics and Dentofacial Orthopedics. This is a peer-reviewed, highest impact factor journal, international journal in the specialty of orthodontics. All right. So there's a process called crystal growth, which was described by Major and Smith. What happens in this? The calcium reacts with the sulfate ion to form as gypsum crystals on the surface of the tooth. These crystals, which are 20 micrometer in length and 2 to 5 micrometer in thickness, chemically adhere to the enamel surface and produce a rough retentive surface for the composite resin. Basically, what is happening? You are basically coating the layer of sulfated polyacrylic acid onto the enamel surface. Now the calcium present within the enamel, that is hydroxyapatite crystals, it reacts with the sulfate ion to form gypsum crystals on the surface of the tooth, on the surface of the enamel. Now these gypsum crystals, which are 20 micrometer in length and 2 to 5 micrometer in thickness, they act as a chemical retentive means for the bonding, which can be utilized to enhance the bond strength of the bonded brackets. So this process is known as crystal growth theory. Another method is sandblasting by using aluminum oxide particles. Aluminum oxide, also known as alumina particles. Now I have one more MCQ for you. We have particle size of 50 micrometers at 65 to 70 pound per square inch for 2 to 3 seconds with a sandblasted nozzle held approximately 6 millimeters from the tooth surface. So we have got 2 MCQs from this particular line. So these are direct MCQs. You need to remember these values if you want to score good in your exams. And bonding to unconventional surfaces. Many times we come across surfaces which are not enamel. We come across surfaces which have zirconia crowns. Suppose you are treating an adult patient who already has got some prosthetic work already done in his or her mouth. So there are certain teeth which are covered by PFM crowns, zirconia crowns, even amalgam restorations for that matter, even composite restorations. So you cannot just apply the same bonding process into that. You need to modify your bonding process. So whenever you come across some unconventional surfaces, hydrofluorosilicic acid and a silane coupling agent can be used for ceramic surfaces. A metal primer like 4-methacroloxy, trimallitate anhydride, methyl methacrylate primer, that is 4-meta-MMA, can be used to bond brackets to amalgam restorations. Please, it's a sincere request. I cannot do anything about it. You need to remember these terms, these molecules, because I've seen certain MCQs coming directly from this particular slide. That's why I have made it a point to incorporate these particular chemicals: hydrofluorosilicic acid, silane coupling agent for ceramic surfaces, and 4-meta-MMA for amalgam surfaces. Okay, so please make a note of it. Now this figure shows steps in direct bonding. What are the different steps in bonding? So first and the foremost, you need to clean the teeth surface using pumice powder, oral prophylaxis and pumice powder. The second is application of etchant, that is the application of etchant using 37% phosphoric acid, or in case when we encounter fluorosis, then you can go for hydrofluoric acid, 9% hydrofluoric acid etching. Now after etching, the third step is washing of the etchant using running water for at least 10 to 20 seconds per tooth. air drying it, you will observe a frosty appearance of the enamel. Then after that, you need to apply the bonding agent, that is called priming of the enamel surface. Okay, I'll write down. First is cleaning and polishing, followed by conditioning of the enamel. Conditioning meaning etchant, application of etchant. This is followed by priming. Priming means application of bonding agent. This is followed by application of the brackets. This is followed by application of the brackets. And any excess adhesive material is removed. That is called flash, is removed using a hand scaler or sickle cell scaler. And finally, light curing the brackets into on whenever they are placed onto the tooth surface. Light cure. So this is how you bond the brackets on the tooth surface. Steps in indirect bonding. That was for direct bonding, when you are applying the adhesive directly onto the teeth surface. In certain practices where the primary objective is, you have got so much rush of patients, multiple patients are waiting outside for the appointment, so you need to go for indirect bonding. So this process is done in the lab. So what is done? You take an impression, you make a dental cast, then you send it to the lab. The lab technician will place the brackets onto the teeth of the dental cast, right? Then after that, a polyvinyl siloxane impression is taken. When the polyvinyl siloxane impression is taken of the cast, same cast, the same process is followed: etching, followed by priming, followed by application of adhesive onto the undersurface of the brackets. Then the same bracket, the transparent tray, it is used to transfer the brackets onto the tooth surface. So this is the tray I'm talking about. Here you can see application of the operator is applying the orthodontic adhesive on the undersurface of the brackets, and it is transferred to the teeth surface. After the conditioning and priming of the enamel has been done, and finally you air dry, you light cure, and then you remove it completely. And this is the final result what you get. That means all the brackets are bonded onto the teeth at a in a very small, very short chair side time. Now, since we are talking about bonding, we'll be talking about bonding materials used in orthodontics as well. So we have got different adhesive systems and their properties. We have got glass ionomer cement, we have got composite resins, we have got polyacid modified composite resins, and we have got resin modified glass ionomer cements. So these are the 4 types of materials which are most commonly used in practices world over for bonding the orthodontic brackets onto the tooth surface. So talking about the glass ionomer cement, this table shows the primary differences between the different types of adhesive materials. So I would want you to please make a note of it. So in glass ionomer cement, the matrix precursor is a polyalkanoic acid, whereas in composite resin, that is some dimethacrylate monomers, right? Then filler particles in composite resin is the silica, since it's a composite, hence the filler particle is quartz, that is silica. Whereas in case of GIC, resin modified glass ionomer cement, that is the aluminosilicate glass particle, that is the primary filler material of the bulk. Size of the particle can range anywhere between 0.05 to 5 micrometer to more than 10 micrometer. Setting reaction, acid-base reaction. But in case of composite resin, we have got addition polymerization, which can be light or chemically activated. Light activated, why? Because this light activation is the most commonly used process world over. You apply a wavelength, blue light wavelength having 484 nanometer of the blue light onto the composite resin, and this blue light, it activates the polymerization reaction within the adhesive. Then particle matrix interface, we have silica gel and we have silane coupling agent in case of composite resins. Okay, so composite resin is the most commonly used material for bonding of brackets onto the teeth. So we have got chemical cure two-phase system and a primer light cure system, that is a single phase system. That can be chemically cured, that is called self-adhesive, and second is called light cure, that is called light adhesive composite adhesive material. Okay. Now, as I was saying earlier, what are the different curing systems used in orthodontics? We have got self-cure composite, that is available as a two-phase system, where initiator is 1 to or 2% benzoyl peroxide free radical initiator, and activator is dihydroxyethyl paratoluidine activator. And setting reaction is initiated when the two pastes are mixed together. Whereas the light cured system, that is visible light cured system, is available as a single paste system, where initiator is alpha 1,2 diketone benzyl, or it's also known as camphoroquinone. This is the primary initiator of the polymerization reaction, and activator is the visible light. And dual cure composite means the setting reaction is initiated by light activation, and polymerization in the depth of the resin where light cannot reach is by chemical cure. Hence the term dual cure resin system. This is also an important box. Please remember the names of these initiators, activators. Okay, please remember the names. Now coming to cements used in orthodontics. Cements, why are they used? They can be used for cementing the orthodontic bands onto the molars. So we have got zinc phosphate cement, zinc polycarboxylate cement, and glass ionomer cement. Now glass ionomer cement can also be light cured or chemically cured resin reinforced glass ionomer cements, and polyacid modified composite resins, which are preferred for luting of orthodontic bands, which create a chemical bond with the enamel of the teeth. Okay, so we prefer glass ionomer cement over any other type of cement, specifically for cementing the orthodontic bands onto the teeth surface, because it's a glass ionomer cement which creates a chemical bond between the enamel and the band. Okay. The clinical significance, that's something called frozen slab technique, where working time can be increased by keeping the mixing slab and powder in the refrigerator, but liquid should not be kept in the refrigerator. So this is a clinical situation where you want to increase the working time. You're mixing the cement on your glass slab, and then you want to increase the working time. So this is what you can do. This is just a clinical tip for you guys. Now coming to an important part, that is orthodontic wires. Orthodontic wires are an integral part of orthodontic armamentarium, because without orthodontic wires you cannot function in an orthodontic laboratory or in an orthodontic operatory for that matter. Now, what are the desirable properties of any orthodontic arch wires? It should be stiff enough, and stiffness is inversely proportional to springiness of the wire. Then we have low modulus of elasticity, or Young's modulus of elasticity should be quite low. It should not be too high. It should have a low load deflection rate. What are these? I'll be talking about them. It should have moderate amount of modulus of resilience, range of activation, range of deflection or large working range, that is maximum elastic deflection, maximum flexibility, or higher spring back. These are the desirable properties in an orthodontic arch wire. It should have high strength, high formability. It should be weldable or solderable, that is joinability. It should be heat treatable. It should have low friction. It should be biocompatible with the oral tissues. It should be resistant to tarnish and corrosion, and of course it should be inexpensive. It should be within the patient's budget, right? So these are the desirable properties of any orthodontic wire, which has to be used for carrying out any orthodontic treatment. Now a small recap. I know this has been taught to you in the topic on dental materials, so still for your reference, so this is something called stress strain curve. stress strain curve, right? So on the y-axis we are plotting the stress, and on the x-axis you are plotting the strain. This is strain. What is strain? Strain is the changing length per unit length of time, right? That is called strain. So whatever amount of change in the dimension you have obtained, that is divided by the original length of that particular wire. That is called strain, and that is expressed as a percentage value. So once you plot this stress and strain on x and y axis, you will observe that up to a certain limit, the graph goes in a linear direction up to a certain point. So that certain point is known as proportional limit. After the proportional limit, this point is called the proportional limit. Now, after the proportional limit, what is the meaning of proportional limit? It's a point till where, even after removal of the stress, the wire returns to its original form. The wire, it returns to its original length. That means there is no plastic change in the structure of the wire. So till that point, that is known as proportional limit. Beyond that, whatever strain the wire is encountering, that is mandatory, that is mandated, that the wire is not going to come back to its original point, no matter whatever happens. There will be some amount of permanent deformation which will be observed in the wire. Okay, so that point is called yield strength. That is called yield strength. Now, beyond the yield strength, even if you stretch the wire even beyond that, at one point, the wire is going to break. That is called ultimate tensile strength, or that is also known as failure point. Okay. Now, if you plot a graph, and if you do integral and differential calculus, so the area under the graph up till the proportional limit is known as resilience. So what is resilience? The resilience is the relative amount of energy per unit volume released on unloading of the test specimen. This is the definition of resilience. And the complete area from point A to point B, that means the complete area within the graph, that is known as formability. Now, formability is the ability of a material to undergo plastic deformation to a given shape without being damaged. Metal is able to undergo a large amount of strain hardening. Okay, so that is the formability. Formability is a capability of a material to undergo plastic deformation to a given shape without being damaged. Now, if you look at this particular stress strain curve, if you plot force on the y-axis and the amount of elastic deformation on the x-axis, or the amount of strain on the x-axis, you can see the proportional limit we have talked about, yield point we have talked about, failure point we have talked about. This is called ultimate tensile strength also. Now, at yield point, if you release the stresses, you allow the wire to come back, there is 0.1% elastic deformation which is permanently present in the wire now. Now, beyond that, even if you go even further, you extend the wire even further, at single point of time, at the failure point, the wire is going to fracture. The wire is going to fracture. Okay. So what is spring back? Spring back is, according to this graph, it's the point. This is the point till when you can expect some spring back. That means the wire is going to come back to its original configuration. And range, what is called range? Range is till the yield point. Range is till the yield point. All right. Now, looking at this particular diagram, this figure, this is again a stress strain curve. Now, this stress strain curve, till the point it is moving in a linear direction. So the function of that is known as modulus of resilience, and stress upon strain is known as Hooke's law. Okay? And Young modulus is also known as Hooke's law, one and the same thing. Hooke's law and Young's modulus are the same. Okay? Now this this is a very important equation, and I have seen many application based questions coming out of this particular equation. Now what it says, that force generated by any wire is dependent on the fourth power of the diameter of the wire upon, means it is inversely proportional to the cube of the length of the wire. Please understand this. Suppose the diameter of first wire, suppose we say A wire and B wire, the diameter of the wire was 1 millimeter, suppose, and length was, suppose you can say the length of the wire was 10 millimeters, right? This is the diameter, this is the length. And the second wire, the diameter is increased, it is doubled. The diameter becomes 2 millimeters and length is also doubled. Let's say it doubles to 20 millimeters. Now let's see what will be the impact on the force values. In the first wire, the force was proportional to fourth power of the millimeter of the diameter upon cube of the length, that is 10 raised to 3. That means force is proportional to 1 upon 1000, approximately 0.001, whatever units you have, approximately 0.001 gram, you can say it that way. But in the second case, force will be proportional to 2 raised to 4 upon 20 raised to 3, right? That means force will be proportional to 2 raised to 4 means 16, and 20 raised to 3 means 20 into 20 into 20, 400 into 20 equals to 8000, right? So 16 upon 8000 will be the value. This will be how much? So this will be the force, this will be the difference in the force values generated by the wire if the length and diameter of the wire are doubled, in fact. Okay. Now this figure shows a conventional tensile stress strain curve in the plastic deformation region calculated on the basis of initial cross section area of a rod. Now you can see in this case, this is called resilience and that is the toughness. Now this is a proportional limit, ultimate tensile strength of substance A and ultimate tensile strength of substance B. What do you think is more is able to which material do you think is able to withstand more forces before fracturing? So that is obviously substance B is stronger than substance A. All right. Similarly, in this case, if you see, we have material A, material B, and material C. So it exhibits different mechanical properties of 3 different materials, right? So in case of material A, we have proportional limit which is very less. Proportional limit of material A is here, proportional limit of material B is here, and that of C is here, right? Now beyond the proportional limit, in material C, that particular wire, it immediately fractures. That means there is no ultimate tensile strength, it is going to fracture immediately. That means material C is the most brittle out of the 3. Whereas material A, although it is very stiff, as you can see, this particular graph can be denoted for stainless steel wire. Stainless steel is a very stiff material, right? It's a very strong material. It has got very high Young's modulus elasticity and it is not breakable. It cannot break at a particular given force level. For breaking a stainless steel wire, you need to apply much higher level of forces. That means material A is stronger than material C, but material C is more brittle than material A. Did you get the point? Now this figure shows classification of orthodontic arch wires based on their composition. So we have stainless steel wires, alloy wires, titanium alloys. In titanium alloys, again we have alpha titanium and beta titanium. I'll be talking about them later. Nickel titanium, we have austenitic nitide, and M nitide, that is martensitic nitide. Then we have timoleum wires and we have titanium niobium wires. These are all alloys of different materials, and based on the composition, we can easily classify these wires on the basis of the material which are used to fabricate those wires. Now, based on cross section and diameter, we have got round wire, rectangular wire, square wire, and multi-stranded wires. In round wires, we have got different sizes, different diameters which are available. It can range from 0.009 inch to 0.020 inches in diameter. Rectangular can range from 0.016 inches to 21-25 inches wires, and square is available only in one form till now, that is 0.16 into 0.16 inches. And we have got multi-stranded wires. That means there is a single wire in between, and we have got different different wires which are intertwined over each other. So we have got braided wires in this, and we have got coaxial wires in this. So don't worry about them. This is just for your information. I hope you will not get any question out of these. Okay. Now this is an important table again, and I have seen application based MCQs coming out of this very table here. So we have got different physical properties compared based on the composition of the wire. So we are comparing stainless steel, cobalt chromium, nickel titanium, beta titanium, and multi-stranded wires. Now I'll just highlight the most important characteristics of each wire, which should be remembered by you guys. So in stainless steel, we have got very high stiffness and very low friction. These two are the important properties to be remembered. In cobalt chromium wires, we have got nothing much in particular. So we have got low to moderate friction. In nickel titanium wires, we have got very high spring back. Spring back means the flexibility of the wire is very high. I'll be talking about what is shape memory, superelasticity. I'll be talking about that as well. Then it has got poor formability, and it is not at all joinable. It cannot be soldered, neither it can be weldable, neither it can be welded. For beta titanium, we have got good formability. This is important, and it can easily be welded. Okay, so beta titanium can be easily welded, and it has got good formability. That is why beta titanium can be used for fabrication of different types of loops into the arch wire. And multi-stranded wires, they have got high spring back but they do not have good formability. They are poor in formability, and friction characteristics are not known in this. Now many people ask me the question, what about the order of friction in the arch wires? So stainless steel provides the least amount of friction. This is followed by cobalt chromium wire, that is alloy wires. This is followed by nickel titanium wires, and finally it is followed by beta titanium wires, also known as TMA wires. So you can remember it that way. The more the composition of titanium in the wire, higher will be the friction because of some process known as cold welding. I'm not going to much detail what is cold welding. Just remember, friction. This is the sequence. Stainless steel has the least friction, whereas beta titanium has the maximum friction. Okay. Now this figure shows the tensile strength and ductility of a metal as a function of percentage of cold working and annealing time. So what is happening? If you plot the tensile strength along the y-axis, tensile strength and ductility along the y-axis, and percentage of cold working and time of annealing on the x-axis. This is what this particular figure is, what you get as a resulting figure. So what is happening? More the cold working or more the time of annealing, the tensile strength and the ductility, they are inversely related to the cold working and the time of annealing. So because of cold working, what is happening? The ductility of the material reduces. Then during the recovery stage, it starts to increase again. And finally, at the time where the grain growth is seen, you can see that the ductility has reached to its original level. Okay. Now, if we talk about the tensile strength, during cold working, the tensile strength is increasing, and then it reduces at the time when recrystallization takes place, and finally during the time of grain growth, it comes to the least level. Now this is the effect of annealing temperature on the microstructure of cold work metals, as you can see in this micro photograph. This A figure shows cold worked, B figure shows after recovery, C figure shows after recrystallization, and D figure shows after grain growth. So this is what the electron microscopic structure of the crystals look like once they are subjected to different types of processes during the annealing process. Now, what is the clinical application of annealing? The properties of the wires can be altered by varying the amount of cold working and annealing. Steel gets hardened by cold working and is softened with annealing. This is important. Steel gets hardened by cold working and is softened by annealing. Fully annealed wires are soft and highly formable. Examples are ligature wires. And partially annealed wires have got more strength but reduced formability. Okay, so basically you have to remember that steel gets hardened by cold working and softened by annealing. Now we have got a different special type of a stainless steel wire, which are also known as AJ Wilcock wire. AJ Wilcock means it was first made by a person called Alfred James Wilcock by Australia, and hence these kind of wires are also known as Australian arch wires, Australian stainless steel arch wires. So we have got different grades which are available: regular, regular plus, special, special plus, premium, premium plus, and supreme. Okay, so they are available in different lengths, different diameters, and different color codings. So nobody expects you to remember that. I find it difficult to remember that even after so many years of practice and teaching postgraduates in my college. So just forget it. But however, this particular box is important because I have seen direct MCQ coming out of this. So this box shows the types of alloys and the resilience. So we have got color coding of different alloy wires: blue, yellow, green, and red. Blue are soft and they are highly formable. The yellow one is ductile. The green one is semi-resilient, and red one is resilient but has got high spring back qualities. So the application of each color coded alloy wires varies depending on the clinical situation. As in when the situation arises, these color coding wires can be used according to the need of the patient. Now, this is what the different wires are used in the clinical practice. So, what are different uses of arch wires? For initial labeling and aligning, it is done using round wires, round and flexible wires that are called NEET arch wires. So, to carry out any initial labeling and alignment, we always need flexible arch wires, which can be inserted in the bracket slot, and because of the unique properties of NEET, that is spring back, shape memory, and super elasticity, it brings the teeth along with it into normal occlusion. Right? Then we have closing loop arch wires, which are made up of TMA or beta titanium arch wires. So as I said earlier, they are quite formable in nature. They can be easily reconfigured in different shapes, different loops, and each loop has got its different application, different indication in the clinical practice scenario. Then for providing torque into the wires, into the teeth, we go to rectangular arch wires. And for intrusion purposes also, we can go for rectangular arch wires made up of beta titanium or TMA arch wires. Now there is a particular property which is unique to night tie, that is called twinning. I was asked this question in my AIMS entrance exam, which I got wrong because I was not aware what is twinning. But I did a mistake. I don't want you guys to make a mistake. So that's why I'm telling you twinning is a property which is unique to nickel titanium arch wires. Okay. Now, what is twinning basically? Okay, before that, let's have a brief description about the history. Now, nickel titanium was first invented by William R. Buckler at Naval Ordnance Laboratory. Please remember this. This is a direct MCQ question. And it is introduced to orthodontic community by Anderson in the year 1971. That's why it is also known as nitinol wire. Niti means nickel, titanium, and nol means Naval Ordnance Laboratory. That's why it is synonymously also known as nitinol arch wires. Now you know that nickel titanium exists in two crystal form. One is austenitic phase, which has got BCC crystal orientation, and one is the martensitic orientation. So we have got austenitic phase and martensitic phase, which are convertible, which are interconvertible, depending on the amount of forces which are generated on, which are liberated or which are subjected to these arch wires, right? So in the austenitic phase, all the crystals are in the BCC formation. BCC is body centered cubic, right? Whereas in the martensitic orientation, they have got alternate orientation separated by a twin boundary. Now, as you can see here, this is the arch wire. Arch wire is quite straight initially. You just bend that arch wire. I have this pen. This is straight, right? I try to bend it. I'll break it otherwise. I'm not bending it here. So if I bend it, at one point of time, the bend is such that the austenite gets converted into martensite because of the forces generated onto the wire because of my muscular energy, right? But that happens later on. Before that, what is happening? The austenitic phase gets converted into martensitic phase by something called twinning. So you can see as you can see in this figure, you can see here, this is the original atom position. This is the original atom position. If I apply some forces in this direction at the lower end of the wire, so if I apply force here in this direction and opposite force in the lower direction, so there is a small plane that is called a twinning plane. This plane is known as twinning plane, which acts as a same plane. Which acts as a mirror, which will let the mirror formation, the mirror image of the atom which are placed above this plane, and the mirror image of the atoms placed below that plane. So that process is known as twinning, and this is known as twinning plane. Now, as soon as the forces are removed, these atoms tend to come back to its original configuration. All right. Okay, let me just read it out for you. The dashed lines show the orientation of the crystal if twinning had not occurred. Note that the atoms on either side of the two, this is important. Note that the atoms on either side of the two twinning planes have a mirror relationship. A lattice structure before and after plastic deformation of a metal by twinning under tension. Note that the shape of the object has changed, but the relative position of the atoms have remained unchanged. Also note that the atoms on either side of the twinning planes have a mirror relationship to each other. That is what I was talking about. Hence, this property called twinning is unique to nickel titanium arch wires. Please remember that. Now, one more thing. Till now, we have been talking about the application of forces. But what happens when heat is applied? So, there is external forces forces are given in this direction. So the top surface, the top layer of the atoms, they get deformed into a different configuration. Even then, if the forces are even then the forces are continuously being given, so the entire crystal gets deformed into this structure, But as soon as the heat is applied, what happens? The deformed crystal gets converted back to its original structure. This is the original one, and this was the deformed one, right? So this is what happens whenever the heat is applied to a martensitic crystal. It gets converted to the original structure, and this is the fundamental principle behind the working of copper nitrile arch wires. I'll be talking about that also. So this figure shows a schematic representation of twinning occurring in nickel titanium alloys for the reversible transformation between austenitic and martensitic nitrile. What is happening? Whenever the forces are being given, this is the interface. So above this interface, there is formation of martensitic nitrile, and below that, the austenitic nitrile gets formed. And till the time the forces are being given, the forces are being generated onto the wire, the entire crystal structure gets converted from austenitic to martensitic. And as soon as the forces are released, this gets converted back to austenitic later on. So this process is known as superelasticity. All right, so coming to this particular graph, so this graph is plotted against a bending moment against the angular deflection of nickel titanium arch wire. So as you can see in this graph, certain sections are present here. So A to B, it represents initial loading. That means you can say that in the initial stage, the nitrile was present in the austenitic crystal form. Now, after the initial loading, the B to C graph, this is known as phase transformation. That means austenitic is getting converted into martensitic form by a process known as twinning. And as I said earlier, austenite, when subjected to any external forces, external compression forces, external shearing forces, shearing stresses, the austenitic form gets converted into martensitic form. So this corresponds to C to D corresponds to permanent deformation, and at the point D, the martensitic form is completely formed, right? Then as soon as you begin unloading, that means at the time of placing the arch wire in a crowded teeth, you are first initially loading the arch wire. During the time of loading, the phase transformation occurs from austenitic to martensitic form, and you have finally attached the arch wire into the bracket slot, into the irregular teeth bracket slot. Then as the wire comes back to austenitic form from the martensitic form, it brings the tooth along with it. So this process, from permanent deformation, the region D to E corresponds to initial unloading. That means martensitic form is getting ready to get converted into austenitic form. Then again E to F, the same process undergoes, that is martensitic form is getting converted into austenitic form. And finally, the portion G to F, corresponds to final stage of unloading. Final unloading stages. So this process, this particular graph is also known as phase transformation graph. This is known as phase transformation graph, right? So basically what is being shown here, austenite gets converted into martensite when subjected to any external forces, and as the external forces are liberated, as the tooth moves through the oral cavity into its proper orientation within the mouth, the martensitic forms get initially unloaded, finally unloaded to form the austenitic form. That means what is happening? Austenite to martensite and martensite to austenite. So this is known as phase transformation. Now, very similar to this, another property unique to NiTi wires is known as shape memory effect or shape memory process. Now, what is happening here? The austenite crystal, it is stable at a higher temperature and can be plastically deformed to some desired shape without altering its crystalline structure. Now, when austenite, it is subjected to some cooling temperature. That means if the austenite wire is kept on a ice slab, or it is kept on a glass slab which has been cooled in a refrigerator. Now, because of that cooling effect, the austenite, it gets converted to a twinned martensite without undergoing a change of shape. That means austenite upon cooling gets converted into twinned martensite. I've talked about what twinning is earlier. Remember? Now, after that, you can see in this particular architecture here and here, you can see that the shape of the wire has not changed. It's only the change in the relative orientation of the atoms in between them that has changed, and that change has been brought about by a process known as twinning. Right? Note that the overall shape of the object has changed, but the relative position between the atoms has not changed. Okay. Now after that, upon heating to body temperature, for orthodontic wire, the deformed martensite, that is a detwinned martensite, will revert back to austenite and regain its original shape. That means upon heating to body temperature, now if one more thing, now if the cooling has resulted in formation of twin martensite, and the twin martensite, if it is again deformed further, it forms a deformed martensite. So that is deformed martensite means whenever the nickel titanium wire is subjected to any shearing stresses, any external forces, it changes its structure, it changes its configuration, it changes its spatial arrangement of the atoms within the crystal lattice, right? And finally, heating of the twin martensite will also recover the austenite crystal. That means one deformed martensite is heated. It is heated. Upon heating, the deformed martensite will come back to the original form of austenite. So this process is known as shape memory effect. Now this graph shows the load deflection curve of the austenitic NiTi wire. Now what is happening? In this case, you can see when phase transition occurs due to stress, the elasticity is termed as superelasticity or pseudoelasticity. Now, as I said earlier, shape memory and superelasticity are two unique properties specifically reserved for NiTi arch wires, right? So when you are activating the arch wire, it is activated up to say 80 degrees. This is the 80 degrees, and then you deactivate it. You just leave the wire to come back to its original configuration gradually with time. Now, upon deactivation, what is happening? Some amount of energy is lost. As you can see, the loading and unloading of the austenitic NiTi wire is not the same, indicating some energy loss, which is known as hysteresis. This process of energy loss to the surrounding environment is known as hysteresis. Okay, so please make a note. This is again MCQ based question to you guys. Now, clinical significance for nickel titanium wire. When a nitinol arch wire is activated over a considerable range of deflection, the forces produced are relatively constant. This means that the arch wire would exert the same amount of force whether deflected over a small or a large distance. This is an extremely desirable property because very low and constant forces for tooth movement are provided by the arch wire during tooth movement, and this is what is desirable because we always want, as we have talked about in the chapter on biology of tooth movement, it's always the physiologically light forces which can easily be tolerated by the oral structures that are the most desirable during the delivery of forces to the oral structures, oral tissues, right? Now coming to beta titanium and other titanium alloys, pure titanium exists in two forms, that is alpha phase and beta phase. Now this second line is important. At temperatures above 885 degrees Celsius or 1615 degree Fahrenheit, pure titanium exists in a body-centered cubic system known as beta phase, whereas at temperatures below 885 degrees, at room temperature, it exists as a hexagonal closed-packed crystal structure known as alpha phase. That means at temperature above 885 degrees Celsius, it exists as a beta titanium phase, which is body centered cubic structure, and at temperature below 885 degrees Celsius or even at room temperature, it exists as alpha titanium phase, which has hexagonal closed packed crystal lattice. Okay. Now Burstone and Goldberg, they were the two pioneers who developed beta titanium with molybdenum, which stabilizes the crystal in beta phase even at room temperature. Now you can ask me a question: if alpha phase exists at room temperature, why do we use beta titanium at all? How is it possible to even exist at room temperature? Well, the answer lies here, that Burstone and Goldberg had added titanium with molybdenum. This is the element they had added, which stabilizes the crystalline beta phase even at room temperature. So this is the reason why beta phase even exists at the room temperature. Now this alloy is also known as beta titanium alloy, titanium molybdenum alloy, or beta stabilized titanium alloy. All these are synonymous with each other. Okay, and other titanium alloys include titanium niobium alloys and timoleum alloys. Now coming to elastics and elastomerics. So these are orthodontic auxiliaries actually. Orthodontic auxiliaries which can be used in the orthodontic armamentarium. So we have intraoral elastics, we have extraoral elastics. We have elastomeric ligature modules which are used to connect the ligate, the arch wire with the bracket. Then elastomeric separators which are used for temporary separation of teeth before banding appointment takes place. Then we have elastomeric chains which can be continuous, short filament, long filament, elastomeric links, elastomeric threads, elastomeric arch wire sleeves, and elastomeric wedges. Even these can be used for correction of any rotation which are present specifically in the upper and lower anterior dentition. What are the clinical applications of elastics? We can have class 1, class 2, class 3 elastics. Class 1, class 2, class 3 elastics. We have studied about them in the chapter on anchorage before. That is intermaxillary elastics, which is also known as Baker's anchorage. Then elastics can also be reconfigured in different alphabets or in different configuration for very specific purposes, like settling of the occlusion, for rotation correction, and the like. So the elastics can be put in vertical manner to correct the open bite, that is box elastics can be used. Then we can use it in the form of triangle, then zigzag, cross bite, cross palette. So these are known as buffalo elastics. Cross palette elastics are also known as buffalo elastics, which can be used to correct the scissor bite in the molar region. Then open bite elastics, asymmetrical elastics, lingual and finishing elastics, right? And even extra oral elastics, which can be used with reversible headgears for orthopedic traction of the midface. We had talked about that in the chapter on orthopedic appliances earlier. And they are made up of natural rubber known as latex elastics. But nowadays, natural rubber, it can be used, but nowadays it is synthetic rubber, which is used in the fabrication of elastics, which is the polymer is cis-1,4 polyisoprene. This is the substance which is used for manufacturing of elastics in today's date. Now, one MCQ which I have come across earlier, Which of the following is a cytotoxic additive in orthodontic elastics? Cytotoxic adhesive, not adhesive, cytotoxic additive. That means this substance is going to cause some deleterious effect. It can be toxic to the surrounding structures. Options were hydrogen sulfide, N-nitrobutylamine, PMMA, that is polymethyl methacrylate, and polyether. So the correct answer will be N-nitrobutylamine. This is the correct answer. This substance acts as a cytotoxic additive in orthodontic elastics. Now, just to name a few, these are elastomeric chains. This is continuous. This is short. And this is long filament E-chains. Then we have elastomeric separators, as I said earlier. Then these are elastomeric modules. Then these are rotation wedges for rotation correction. And these are elastics. So all of these are orthodontic auxiliaries made up of elastics, natural elastics. Now we have talked about earlier, class 2 elastics and class 3 elastics are types of intermaxillary elastics which take this which is named as Baker's anchorage. We have talked about that earlier. Now, what are the various applications of elastics? We have talked about it earlier: zigzag elastic, box, settling, diagonal, check elastics, class 1, class 2, class 3 elastics. So all these different configurations of elastics have different purposes. You can read that in the box given below. Coming to magnets. Now, magnets have found their profound use in orthodontic practice lately. In fact, it was not used earlier, but with time, different people, different researchers, different authors have come up with their own proposals of using magnets in different clinical situations. So, first of all, what is the composition of magnets? They are made up of rare earth elements like samarium cobalt and neodymium iron boron magnets, right? So these are also cytotoxic because a byproduct of these materials can be cytotoxic. So the magnets are always coated by a substance called parylene whenever they are used intraorally. So this substance, parylene, it's like Teflon, not exactly Teflon, it is like Teflon, a sister molecule of Teflon, which does not allow leaching of byproducts into the surrounding oral structures. Now, Darren DeLisle was a person who was a pioneer in the usage of magnets in orthodontics. So, what are the clinical applications? They can be used in magnetic functional appliances and growth guidance, for intrusion of teeth, for retraction of canine, in arch expansion, molar distalization, space control, disimpaction, correction of class 2 bimax protrusion, orthodontic extrusion of fractured crown root, and as well for retainer purposes, right? Now, what are the parts of fixed appliances just to conclude this particular chapter? So we have got orthodontic bands, which come in different thicknesses in the posterior, in the anterior region. Then attachments for orthodontic bands, where we have weldable or tooth surface which are bondable. We have bracket systems. The most commonly used brackets in today's world are MBT system. We have got other bracket systems like rod system, baked bracket system, pre-adjusted edgewise appliance, tip edge appliance, lingual appliance, Damon appliance, incognito, insignia. Many different types of appliances have come up recently. Then we have buccal tubes, which can be rectangular tubes, round tubes, flat oval tubes, double tube, triple tube, eyelets, cleats, buttons, arch wires we have already talked about earlier, which are preformed, which are available in different cross sections, round, square, or rectangular form. They can be single stranded or multi stranded. They can be made up of stainless steel, nickel titanium, TMA wires, alloy wires, and they could be plain or looped arch wires as well. Now and then we have assisting elements like small instruments, small armamentarium, which can be helpful, which can be handy in correcting certain types of malocclusion, like open or close coil springs for opening the space, closing the spaces between the teeth, uprighting and rotation springs, crimpable hooks, Stainless steel ligature wires, we have talked about earlier. Elastomeric modules, I have talked about. Lock pins, separators, rubber bands, bonding adhesives, cements, and removables, certain other removable appliances. Right? So, these boxes show the disadvantages of banding and what were the advantages of bonding. Disadvantages of banding, you can see we have anesthetic appearance, we have inaccurate bracket positioning, and increased chairside time. That means more amount of time is required for banding the molar bands into the teeth. Whereas advantages of bonding include less chairside time, accuracy of bracket positioning is improved, arch length is not altered as in banding, because we need to separate the teeth temporarily, so that in that separated portion a band can be cemented, so that leads to increase in the arch length, the linear distance, anteroposterior distance, rising from the distal of the first molar to the interincisal. So this is the arch length, and it is more hygienic. There's less patient discomfort, and very less amount of enamel needs to be etched while bonding. All right. So that completes a lengthy chapter, an important one in fact. Should you have any doubt, you are very much welcome to ask me, or through Telegram group or through Facebook group. I'll be very happy to answer your queries.